We continue with section 5.4, and we're going to look at remark 5.4.2. And it says, in theorem 5.4.1 that we have just proved, the roles of x and y can be interchanged. So if we consider a vector function r from the closed interval ab to r2, such that r of t is equal to x of t, y of t, so that the derivative exists on the open interval ab and is continuous at a point c in the interval ab. So if y is y prime, so if the derivative at at c exists, the derivative y prime at c exists, then there exists a real number delta greater than 0 and an open interval I containing y of c and a function g from I to the real numbers, so that for every t that you pick in the neighborhood of c, r of t is equal to y of t if and only if x is equal to f of y. So basically what this is saying is, if we interchange the rows of x and y such that we know that the derivative of r of t exists and y prime of c is not equal to 0, then we can also still have the same scenario where instead of having y is equal to f of x, now we will have x is equal to f of y for some y in the interval, and then x a real number. And then if we look at the derivative, so furthermore, g is differentiable on the interval I, and g prime of y is equal to, so instead of having y prime of t over x prime of t, we now have x prime of t over y prime of t, and then we get that where y is equal to y of t in the interval I, and then t is in the neighborhood of c. Right. Let's look at the next remark, and this is remark 5.4.3. So let r, a closed interval a, b, and c be given as in the theorem 5.4.2. A particularly important case is when x prime of c is not equal to 0 and y prime of c is equal to 0. So in this case, according to theorem 5.4.1, a small piece of the curve around the point r of c is the graph y which is equal to f of x, because you just apply the theorem 5.4.2, and this graph is a differentiable function. Well, the graph of the function, so the small piece of the curve around the point r of c is the graph of a differentiable function f, and f prime of x of c will be equal to y prime of c over x prime of c, which is equal to 0, right? And therefore the tangent line to the curve at r of c will be horizontal, right? And if x prime of c is equal to y prime of c, then neither the theorem 5.4.1 nor remark 5.4.2 will apply, right? Because we need one of them to at least be not be equal to 0, right? And so the idea here is, if x prime of c is not equal to 0, then we can use theorem 5.4.2, and if y prime of c is not equal to 0, then we can use remark 5.2. But if both are 0, then all these two results will not apply. So what do? we need to be able to investigate further to determine the behavior of the curve at that point, right? So this is an important thing to note. Let's look at example 5.4.4, and we sketch the curve C with parameterization r of t is equal to t cubed minus 3t and t squared. This is supposed to be looking that way, and the function is defined, or r of t is defined where t is between minus 2 and 2, inclusive of minus 2 and 2. So for the solution, so we are going to consider values of t in the interval minus 2 to 2, because we are told this curve has this parameterization where the t is between this and that, minus 2 and 2. So we are not going to be worried about all the other values that are not between minus 2 and 2. Right, and so the first thing we need to think about is the endpoints. So what are the endpoints? So if we put the minus 2, we get r of minus 2, it becomes minus 2, 4. So it's just a matter of substitution. Where there's a t, you put minus 2. And then where there's a t, you put 2 for us to get the endpoints. And so we get minus 2, 4, and then 2, 4 as our endpoints. And then the next thing is we need to think about y-intercepts. So how do we get our y-intercepts? So we set the function x of t to be equal to 0. So x of t is equal to t cubed minus 3t, which is equal to 0. And then we solve for t, and then we find out that we've got these three roots of the polynomial. So we get t is equal to 0, t is equal to plus or minus root 3, right? And so now we know where the intercepts are. Well, so we need so therefore the y-intercepts are going to be at, so if we put r of 0, we get 0, 0, and then so why are we putting 0? T is equal to 0, and then if we put r of root 3, we get that is equal to 0, 3. Here it's supposed to be r of minus root 3, not the square root. The square root is supposed to be brackets. So r of minus root 3 will also still give us 0, 3. So we've got two intercepts only, even though we found that t is 3 values. These two give the same gives the same point, 0, 3, right? And then for x-intercepts, we take y of t and we equate it to 0, and then we see that t is equal to 0. So therefore the x-intercept will be r of 0, which is the origin, 0, 0, right? So it is the y-intercept, it is a y-intercept and an x-intercept. This point 0, 0, that is important to note when we are trying to draw our graph. So determine any point. So we want to now find the turning points. Determine any possible points in the curve, that is points, um, this is possible turning points, and points on the curve where the tangent line is either horizontal or vertical. So we might have horizontal tangents and vertical tangents. Now according to remark 5.4.3, for a horizontal tangent we must find t between the open interval minus 2 and 2, such that if we take the derivative of y prime of t, we will get 0. We equate it to 0, and then we take the first derivative of x of t, and we also we want it not to be equal to 0. That's when we can get a horizontal tangent. We will talk about what we need for a vertical tangent, right? And so x prime of t will be equal to 0 if and only if t is equal to 0. And in this case, x prime of 0, I think this is supposed to be y prime of 0, right? Sorry, x prime of t is equal to 0 if and only if t is equal to 0. I think that statement is supposed to be y prime of 0. So it's supposed to be y prime of 0 here if and only if t is equal to 0. And x prime of 0 is equal to minus 3, which we know is not equal to 0. So therefore we have a horizontal tangent at r of 0, which is the origin. So and then we call that 5.7. We are going to need it. And then for a vertical tangent, we find t between minus 2 and 2, so such that in this time we want x prime of t to be equal to 0, and then y prime of t not equal to 0. And then so if we find this, we will find that x prime of t is equal to 0 if and only if t is equal to minus 1 or t is equal to 1. And then if we calculate y prime of minus 1 and plus 1, we also get plus or minus 2, which is not equal to 0. So therefore we do have a vertical tangent, and it is at, so if we put r of minus 1, we get 2 1, and then if we put r of 1, we get minus 2 1, right? So we've got two tangent two vertical tangents to the curve, right? And then so now once we get all that information, we need to then connect the dots. We can plot our points. So these are the end points there, and then these are the intercepts that we found, right? And then we know this is a turning point where we've got a horizontal tangent, and then on these points is where we've got the vertical tangents, right? You remember the last time, the last point was we've got 2 1 and minus 2 1. So those are the points where we've got that. So with this information, what we just need to then do is to connect the dots. So from there we can then move and see that, okay, for this to make sense, it has to look like this. So that is that for example 5.4.4. Now let's look at 5.4.5. So we sketch the curve parameterized by r of t, which is given by that, and we are also given where the function is, where the curve is defined from minus 3 over 2 to 3 over 2, right? So we start off with endpoints again, and then we find out that these are the endpoints that we need, these two. And then for y-intercepts, we say we take x of t to be equal to 0, and then we find out that that can only happen when t is equal to 0, and then if we put r of 0, we get the origin. So we've got a turning point, sorry, we've got a y-intercept on the origin. Now on the for the x-intercept, we set the function y of t to be equal to 0, and then we solve for um, t, and then so if we say t is equal to, if we solve, we see that t is equal to 0 or t is equal to 2. But remember that our function is defined for between minus 3 over 2 and 3 over 2, so we don't really need this point because it is greater than 3 over 2. It is greater than the curve, the where the curve is defined, right? And hence only the x-intercept of c is at r of 0, which is the origin. So we've got a y-intercept and an x-intercept at the origin. That's what 5.10 and 5.11 are saying. Now to determine the points where the tangent to the curve is horizontal, we determine a t which is in the right interval, where y prime of t is 0 and x prime of t is not equal to 0, right? So if we find the y prime of t equal to 0, we see that that is when t is equal to 1, and we can then check and see that x prime of 1 is equal to 2e, and we know that e is non-zero, so therefore the derivative is not equal to 0. So therefore we've got a horizontal tangent at the point e minus 1. Right. Now we want to look at the vertical tangents, and we set x prime of t to be equal to 0, and y prime of t should not be equal to 0. And so if we say x prime of t is equal to 0, we find out that t is equal to minus 1. And if we put that minus 1 in the function, we in the y component function, we see y of minus 1 is equal to minus 4, which is not equal to 0. So therefore we have a tangent, a vertical tangent at the point e to the minus 1, 3. Right, so now we've got all the information that we need to be able to plot the, the curve. So if we put the points, so we've got the end points there, and then our vertical tangent is on this point, and our horizontal tangent is on this point, and so therefore we're connecting the points, and then we have got our x-intercept and y-intercept there. So therefore, using that information, we can then just connect all the points and get a rough sketch of our curve. Right, so that is that. Let's look at another example, and this is example 5.4.6, where we are given r of t, which is t minus sine t and 1 minus cos t, and t is between minus 2 pi and 2 pi. Right, so the endpoints, again, we start off with endpoints. R of minus 2 pi, we get that. R of 2 pi, we get that. So we know where the curve is starting and ending. And then for y-intercept, we do what we do, x of t is equal to 0. And then we see that that is when t is equal to 0, and then we get that. So furthermore, x prime of t is equal to 1 minus cos t for all non-zero t, so that x of t is less than x of 0 if t is less than 0, and x of t is greater than 0 if x of 0 is x of t is greater than x of 0 if t is greater than 0. So therefore, if x of t is equal to 0, if and only if t is equal to 0. So this shows us that for any other values that we can pick, either x of t is greater than 0 or x of t is less than 0. So the only point where x of t is equal to 0 is when t is equal to 0. And the only y-intercept that we have is the origin. Now let's look at the x-intercept. So for x-intercept, y of t is equal to 1 minus cos t, which is equal to 0. We set it like that, and then we solve for t to find that t is equal to either minus 2 pi, 0, or 2 pi. So hence the x-intercepts are going to be at, so we then put our t's, the respective t's, and then we find out that these three are the x-intercepts. Now to determine the tangents. So to determine the tangents, where the tangent to the curve is horizontal, we are going to assume that y prime of t is equal to 0, and then we want to find values, and then if for that value x prime of t is not equal to 0, then we have what we need. So y prime of t is going to be equal to 0 if and only if t is equal to minus pi or 0 or pi. You can do the calculation here, right? And x prime of 0 is equal to 0. X prime of minus pi is equal to x prime of pi, which is 2. So this one cannot be a horizontal tangent, so the curve only has these horizontal tangents, minus pi over 2 and pi over 2 on those 2 points. Because this one gave us 0, it's not supposed to be 0, right? And then so we need to note that remark 5.4.3 does not give any information on what happens at the points where x prime of t is equal to y prime of t is equal to 0. That is at the point r of 0 is equal to 0, 0. So at this point we don't know what happens at x prime of 0, but we know from what we already know, the information that we have, that these two are definitely horizontal tangents for these two values, or at least for these 2 points we've got horizontal tangents. But at this point we don't know for this one what happens, right? So let's look at how we can go over that. So for minus 2 pi up to 0, for a t between minus 2 pi to 0, x prime of t is not equal to 0, so that this part of the curve is the graph y equals to f of x of a function f, and dy over dx is equal to dy over dt dx over dt, which is equal to sine t over 1 minus cos t. So here we are using the fact that x prime is not equal to 0, so we are able to do this by previous results that we have talked about. And then so using L'Hospital's rule, we can say the limit as t tends to 0 from the left of dy over dx becomes the limit of cos. So if we differentiate that, we get cos t, and then if we differentiate the bottom, we get sine t, and then that goes to minus infinity. Now in the same way, the limit as t goes from the positive, so we just use the same argument, it is going to go to infinity. So therefore the curve forms a sharp cusp. So if we think about what has happened here, what we are saying is from the negative, it's going to be negative infinity. So the graph it has a negative gradient, and then it's going to be very sharp when it approaches 0. So it's going to be, for it to be minus infinity, it means it goes very sharp. Now if we look at it from the perspective of the other side, it's going to also be positive, and then it increases until it's very sharp, almost vertical, right? So we get this sharp cusp like that. So we check whether or not the curve has any vertical tangents, right? And then for minus 2 to for a t between minus 2 pi and 2 pi, we have that these x prime of t is equal to that. It's not minus here, it's equals to 0 if and only if t is equal to 0, and we have dealt with that point. So the value has already been dealt with, so there are no points where the tangent to the curve is vertical. Now plotting the points that we found, the end points, the turning points, and then the tangents that we have, and thinking about this sharp cusp, we can then easily connect the dots. So we've got our a tangent, a vertical tangent there and there, and then we've got horizontal tangents there and there, and then here we've got this sharp cusp where the 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 derivative becomes minus infinity here, so it's almost vertical, and then plus infinity, almost vertical again. So therefore we then connect the dots and see that our graph looks like that. And that's just a rough sketch. That is all for curve sketching, section 5.4. Thank you.